Right. Uh, let's get this show on the road. Hello. Okay, there we go. Hello, everyone. Hope you're well. Welcome to another edition of Math 1000. You might hear some noise in the background, a little bit of drilling going on in my building. Nothing I can do about that at the moment, but hopefully it's not too loud so that you can't hear me. Hopefully you can hear my voice well enough so far. Let's actually jump into it. Let me share my screen from so hopefully you can see my screen. Let me make sure that I can see the chat. And I think we're good to go. Okay, so the agenda for today, let me just double check. Okay, I think we're fine. Okay, so the agenda for today, we are going to go over the quiz that you had on Monday. So we're pretty much gonna run through everything here. And then at the end, if you have any questions, we might have a short Q&A session towards the end. So yeah, let's just actually jump into it. So I'm not gonna do the polling thing. What I'll do is I'll go through these on my own for the most part, but I will be asking for your input every now and then. So please don't feel too shy to chime in whenever I ask for your input. Also, if I'm doing something and you don't get it, don't be afraid to chime in and ask a question. So you can stop me at any point. I want to make sure that everyone's following along. So please chime in with questions or comments if you have them. That being said, let's actually go through these. The first few, however, these are more or less rules that you kind of should just know. Well, not question two, but question one is more or less just some rules that you should basically just know. And so nothing really much to talk about here. So let's actually just go through these. First one, a raised to the power of x over y, a to the x over y. Maybe someone can tell me what this should be? Anyone? Are you guys hearing me?
Radical a to the x, and then you put the y on outside of the radical.
I don't know if it's me, but you sound very low.
I'm sorry, I said a to the x in a radical, and then you put the y outside of the radical on the left.
Okay, so that the y is on the outside of the radical, so that looks like this option right here.
Right.
And that would be correct. Okay, so maybe I could even boost this just a little bit. Okay, yes, that's correct. What about the second one? M to the x plus y. What is that?
M to the x times m to the y.
That's this one. A to the minus n.
1 over a to the n.
Right, so this is 1 over a to the n, which is none of these options here. M squared minus n squared.
Professor, wasn't 1 over a to the n b?
It is. Somehow I missed that one. Yes. All right. Thanks for chiming in. M squared minus n squared. What is m squared minus n squared? Formula for that.
The m minus n squared, parentheses.
As in the second option here?
Yes. Is that it?
No.
Wouldn't it be m plus n parentheses and then times m minus n, so it's none of the above?
Right. So this is the difference of squares formula. So it's none of the above. It's definitely not any of the above either. So this classic mistake here is this would be a distribution of powers across some error. So I might have caught a few people with that. I don't know. I don't think people make the other mistakes very often, but I know B would be a semi-common mistake. It's actually none of the above. Moving on to m cubed plus n cubed. What do you think that is? Anyone? So I mean, spoiler alert, this is the sum of two cubes formula, sum of cubes formula. Does anyone remember that?
That'd be the third one.
It is not the third one. However, that would be a common error.
Isn't it D or the fourth one? Because you need to cancel out the two mn in the middle.
It's this here would be a common error. What's the problem? What's wrong with the fourth one?
The negative?
No, there should be a negative. The 2 is the thing that students often, like for whatever reason, I think they just think of the all squared formula, a plus b all squared is a squared plus 2ab plus b squared. So whenever they expand something like that, they tend to put the 2 in the middle, but there should actually not be a 2 in the middle. This would actually be m plus n times m squared minus mn plus n squared. There's no 2 in the middle. So this one is actually none of the above. Okay, so these are just some rules that you should actually know, and I put a couple issues with some common errors that students might make, but these are the correct. If the correct choices were not there, I wrote them on the tile here, but yeah. So question two is the first one where we had to do some sort of calculation. It's not really a general formula. How do we go about finding the GCF?
It's 3x to the negative 1/2.
Right, so it's going to be 3x to the negative 1/2. So this is just a product of all common factors raised to the lowest, it's always the lowest power to which they appear. So here, notice what you have. You have 3x to the 3 over 2 minus 9. 9 you can think of as 3 squared, x to the 1 over 2, plus 6. 6 you can think of as 2 times 3, x to the minus 1/2. So you see 3 is a common term. The powers at which it appears are 1 and 2. Right, the middle term has a 3 squared, the other two terms has 3 to the 1. You pull out the 3 to the 1. Right, you always pull out the lowest power. X is also a common term. X is in everybody. Right, you can see here that X is in every single term. The lowest power to which it appears is negative 1/2. The negative number is going to be smaller than all the positive numbers that appear. So you pull out the x to the minus 1/2. So it's 3x to the minus 1/2. You take the product of all of those common terms to the lowest powers. That gives you what's called the GCF. So that's that one. Let's move down to question 3. How would you factor this completely? So let's actually work through this one.
Subtract 2x to the negative 1/2.
So here we have 2x to the 3 over 2 plus 4x to the 1 over 2 minus 2x to the minus 1/2. Right, what did you say? The
I said,
GCF?
yeah, extract 2 to the negative 1/2, or
Right, 2x to the minus 1/2 is the GCF, which we learned how to do from the last problem. Now you're going to write what's left over inside. Do you remember how we get what's left over inside?
You do x to the 3 over 2 minus negative 1/2.
Right. Whatever you pull out, you have to subtract the powers of those things on the inside. So on the inside here, you'd be left over with x to the 3 over 2 minus the negative 1/2. And technically, you would also have the 2 to the 1 minus 1, but let's not actually write that. But the constants usually don't confuse people. It's usually the power of the variables that confuse people. So when I pull out a 2, the 2 is gone. What is the new power of x that's left over? It's the original power minus the power that you pulled out. Plus, move on to the next term, the 4. If I factored out a 2, there's a 2 left over here. And what is the power that's left? Then that's going to be 1/2 minus the power that was factored out.
that would be 1. Right?
Minus the other one, we have 2 being pulled out. So now what's left over? It's x to the minus 1/2 minus a minus 1. Okay. So this line, you don't have to write this line, but you should know in your head what's going on. So you don't have to write this line. So I just want to explain to you how we're going to get to the next line. So your second line would probably be something like this. 3 over 2 minus a minus 1 over 2, that's just 3 over 2 plus 1 over 2, that's 4 over 2, so that's x squared. The 1/2 minus the minus 1/2 is a half plus a half, so that is just 1. And of course, minus a half minus a half is just 0, so that just becomes that. Right, now once you do that, the initial GCF factor, and you want to see if things can be factored further. So now you're focusing on this guy. Can this be factored further? Yes, no, maybe so. Maybe? Like, how would you know? So the coefficient of the square term is 1. So what is the trick here to see if this can factor?
Method or trial by error method.
Come again?
Sorry, maybe try out the AC method here, I guess, if it would apply.
When do we use the AC method?
When y is greater than 1.
When the coefficient of x squared is not 1. Here the coefficient of x squared is 1, so we don't need the AC method. It's just a regular quadratic. What do you look for to factor a regular quadratic? A monic quadratic, it's called. What do you need here? You need to find
A number that adds to 1, a number that adds to 2 and multiplies to negative 1.
2 numbers that multiply to give negative 1 and add to give positive 2. Right? And it turns out, no such numbers. No such numbers. So it turns out that this cannot be factored further. So it turns out that this is the final answer. And so we look for that up top, and it looks like I was covering the mic just now. Hopefully you were hearing me.
Yeah, we can hear you.
I was trying to cover up the drilling sound a little bit. But yeah, so it's going to be that one. So remember your techniques and when you're supposed to use the techniques. The AC method only comes into play when the coefficient of the squared term is not 1. If the coefficient of the squared term is 1, then you just look for two numbers that multiply to give you the constant term, and then they add to give you the coefficient of the middle term. Okay, let's work through this one together. How do we simplify this based on what we know about exponents?
So the first thing I did was, and I don't remember if I got it right or wrong, but I added the exponents to inside of the parentheses for each one. So
Added? So how did you do that?
So for 3CD to the 6, for the D to the 6, I added 3 to the 6, so 7, 8 to the 9th, so it would have been D to the 9th, and E would have been to the 3rd in there. No?
No. When do we add powers versus
You add powers when you're multiplying bases.
you add powers when you're multiplying, not just multiplying bases, a little bit more specific. So you're telling me if I had a cubed times b to the 5th, I would add the powers?
Oh, you have to make sure the bases are the same.
The bases have to be the same. So we have to know the rules. We add powers if we have two things, we're multiplying two things and the bases are the same. We would add the powers in that case. What is the rule for when I have something to a power and I'm raising that to another power?
You have to distribute the outside power so it would multiply.
You would multiply the powers. Okay, so
Oh.
it's not an addition of powers that should happen here. It's a multiplication of powers. You have to remember these rules. So that being said, and of course there's another rule that goes, well, if I have two things and there's a power on the outside, I can actually multiply the powers across the product, right? This is not true for sums. We spoke about that in lecture 1, but it is true for products. And so that would be the first step here. I would actually take that third power on the outside of the first parentheses, and I would literally multiply all the powers inside. So it's actually d to the 18 because it's 3 times 6. Now with this, I can actually just remove the parentheses.
Professor, I don't think there's an A in the problem.
A?
It was a C.
It was a C.
Yeah.
Yeah.
That's a C. And that's a C. Okay, now what do we do?
Powers of like bases.
You do the what?
You add the powers of the bases that are the same.
Right, by the rules that I just mentioned. You could, to see this more clearly, just rearrange, because multiplication can work in any order. And now you just do each of them. So the 3 cubed is going to be 27. then I would have c to the 7, then I would have d to the 22. And so this part becomes the 27. These multiply to give you that because you add the powers, and these multiply to give you that because you add the powers. So it's 27c to the 7d to the 22. Looks like this guy right here. So, of course, you guys have seen by now that, as I mentioned, memorizing the rules, knowing the rules of the game are very important because that prevents you from making errors. So you need to know, when should I add powers? When should I multiply powers? When should I be doing all these maneuvers that we've learned in class? It's under very specific circumstances, right? So you can add the powers if you're multiplying things of the same base, right? If you're dividing things of the same base, you subtract the bottom power from the top power, right? If you have something to a power raised to another power, you multiply the powers. These are things that you should know. If you have a product of things raised to a power, the power can distribute to each of them, and it multiplies the power of each of the factors inside. So these are just some of the rules that you should know. These are all discussed in class, so just wanted to remind you of that. How would you make sure that this thing factors? Choose a possible middle term. Now, there are a couple ways that you could go about this. You could actually just do a process of elimination, just try all of them and see if you can factor. But there are other ways as well. But maybe that's going to be the way. So you might want to think, can I think of two numbers that when I multiply, I get 20, and when I add them, I get 13? Or when I multiply them, I get 20, when I add them, I get 12? Or when I multiply them, I get 20, when I add them, I get 7? Or when I multiply them, I get 20, when I add them, I get 3, etc. Right? So you can kind of go down the list here.
12x.
So would 12 work? What are the two numbers in this case?
10 and 2.
10 and 2, right? So you'd realize that here, 20, I can think of it as 10 times 2, and these guys here sum to 12. And so, yeah. Right? So again, this is just something that is testing. Do you know the rule of how you would go about factoring a quadratic? What are the things you look for, right? And you can realize that the ways you would factor 20, you can't really get them to add up to any of the other powers, right? Because all of the other guys, the 13, the 7, and the 3 are odd. You can't really factor 20 in such a way that you get those particular odd numbers. I mean, 20 is the same as 4 times 5. So you can get a 9 out of this. So if there was a 9, there might have been an option. But you're not going to be able to get a 13 there, right? So, but yeah, just knowing the rules of how to actually go about factoring a quadratic can actually help you figure that one out. Okay, so now we want to write some of these expressions so that only positive powers appear. And I'll make my usual disclaimer here, because sometimes students, they take algebra and pre-calc classes and they become traumatized. They think that, oh my God, I can never write a negative exponent, or I can never have a radical in the denominator, and it gets them freaked out. In general, this is fine. However, in algebra and pre-calc, because we want you to get used to using the rules and doing these manipulations, we'll sometimes put extra restrictions on them that in general won't be necessary. So while in general there's nothing wrong with writing something to a negative power, here I just want to know, do you understand what it means to have a negative power? Can you manipulate the expression if it has a negative power and rewrite it in some other way? So that's what this is about. How can you rewrite the 5 times x to the minus 2, 5x to the minus 2 as an expression without a negative power?
Maybe the first option, 1 over 5x to the second.
No. Why would the answer be no? Does anyone see why it would not be the first option?
Is it because the 5 and the x squared are being multiplied, so technically they're like two separate terms, so the 5 could stay in the numerator and the x squared would have
Right.
to be in the denominator?
What would this one be? If this is what was intended, how would it have been written? Because this would have to be 1/5
Parentheses around
x to the minus 2.
x.
Well, the parentheses around the 5 and x would actually not give you that. If I had the parentheses around the 5 and the x, like 5x to the minus 2, which one would that be?
The last option.
It would actually be the last option. Because of the parentheses. So here it's like the entire thing gets moved down because this is going to be 1 over 5x squared because the negative power applies to both. And then by our distribution rule, the square gets distributed to the 5 and the x. And so I would end up with 25x squared. Remember, whenever we have a mathematical manipulation like a power, it applies only to the guy immediately to the left, which means if I have 5x to the minus 2, it is assumed that the minus 2 only applies to the x. It does not apply to the 5. If I wanted it to apply to the 5, I would have to indicate that with parentheses. Right? So that's how you do it. So this one is actually the third option, right? Because this is 5 times x to the minus 2 separately. I can apply the rules for negative powers, 5, and put that in the denominator. And then when I multiply them, I get the 5 over x squared. Right? Now, the minus 10x is like nothing. I don't know how you get a minus 10x from here. And the 1 over 25x squared is actually if I were to have the 5x in parentheses, right? So these are just some things. It's very important that you know the notation. And yeah. Okay, what about this? Negative x to the minus 18. First of all, let's work it out directly. I have negative x to the minus 18. What does that mean? And now I have parentheses. If I apply my rules, what does that tell me? What would the first step look like?
X to the 18?
Yeah, you're skipping a step technically though.
Oh, you move it to the bottom, to the
You
denominator.
move it to the bottom. So it becomes 1 over minus x to the 18, right? And now it becomes positive x to the 18 because this just now becomes minus 1 to the 18 times x to the 18. And minus 1 to the 18 is actually positive 1. So it now becomes 1 over x to the 18. It's actually the first option, right? The even power gets rid of the negative sign, which is why the third option would be incorrect. The third something like the third option would be correct if the power was odd. So if it were minus x to the minus 19th, then it would actually simplify into 1 over minus x to the 19th. However, the power is even, so that's why the negative is gone. This one here, I moved it in the denominator, but I kept the power negative. That's not a rule, right? So a to the minus n is 1 over a to the n. You would change the sign. And so, yeah, it's going to be the first one. Okay, so those two were just making sure that you understand notation, how PEMDAS would work with laws of exponents, etc. This one, though, does require some more computational skills. So this is applying more rules. So it's not a very super basic problem. However, if we just pay attention to the rules that we've been given, we should be able to get through this unscathed. Okay, so here, what should we work on first?
Parentheses.
Parentheses, right? So what's inside the parentheses is r to the fourth and r cubed. Can't really do anything. So what's the second thing that we do?
Get rid of the -2. Like,
Okay, and the 3. So so according to PEMDAS, the second thing we should be cared about is figuring out simplifying our exponents, right? So the exponents that need to be simplified is there's the r to the fourth to the cubed in the numerator. So I would first fix that. R to the fourth to the cube would be what?
r to the 12.
R to the 12. We multiply the powers. That's the rule. R to the cube to the -2 would be what?
-6.
-6. Okay, now keep going. Can I simplify the numerator?
Yes.
Yeah, what does that become?
15. R to the 15th.
4r to the 15 because I add the powers. Okay, so now how do I simplify this?
You subtract the r's.
So we subtract the powers of the r's, so what do you have? So now you think of these two as separate things.
You get r to the 21.
Right, so this is r to the 15 minus a -6. And we have the 4 over 15 left over here. So it just becomes 4 over 15 r to the 21.
Would that be in the numerator because it like turned positive? So you could bring it back up?
This one is in the numerator, but it's just because of how I followed the rule. It's possible that the other way around, so let's do the question, the other way around.
Yeah, if you brought
Because I understand where you might have an issue. Suppose we had,
wouldn't it give you the same answer if you brought it up anyways?
no. So let's say the -6 was up here and the 15 was down there. I can still apply the rule. So I leave the 4 over 15 and then I would have r to the -6 minus 15. So what you'd realize by applying this rule, I don't really have to worry about whether or not, this is 21. I don't have to worry about whether or not it's in the numerator and denominator because the power is going to tell me. Now this simplifies to r to the -21. That tells me that that's in the denominator, right? So this one is not in the denominator because the power is positive. This one is in the denominator because the power was negative.
Okay,
so when you're applying that rule of subtracting the powers, you really don't have to consider where it should be because the resulting power is going to tell you.
Okay, thank you.
Right? So you don't have to worry about that. So, and that's one of the power of the rules. So now a very common thing that causes students a lot of errors is that they're concerned with so many things to the point where it causes them to make a mistake because they're trying to balance so many things all at once, when a lot of the times you actually don't have to be concerned with most things that are going on. It's just that you need to zoom in on the rule that's applying to this particular situation, and you just mindlessly apply the rule. And then whatever needs to fall out of that rule will automatically be there by just changing the notation. So here, when I was subtracting powers, there was nothing in the rule that says, oh, you have to worry about who's in the denominator, who's in the numerator. It didn't matter, right? It was just x to the a over x to the b. I don't care what a and b are. Simplifying that becomes x to the a minus b. Afterwards, you can worry about whether the power is positive or negative. Should it be in the numerator? Should it be in the denominator? But here, the power is positive 21. So if I were to write it, it would stay in the numerator.
Professor, quick question. Sorry.
Yes.
Yeah.
So this would be
where you squared out, where you drew square over the 4 and the 15 and the r to the
yes
15th power.
Yes.
And then the negative. Could you just asking? Could you bring up the r -6 up to the numerator, and if not, why?
You could. So you could actually do this. That would also be correct. This is also correct,
Okay.
but there is a caveat. I have found through experience, through grading a lot of papers, in that when students start to do things like they have a bunch of terms and they start switching people, moving things up and moving some things down and swapping based on the signs, they make more errors than if they were to just subtract the powers.
Right.
You know, so if you had a bunch of variables and people say, oh, this is negative, so I can switch it, and then this over here is negative, so I can switch it down, and they start switching things up and down while they're trying to add and subtract powers, it causes needless errors. So I would not worry about it, but switching locations while applying laws of exponents can cause errors if things get too busy. Not recommended in general. You can get away with it here, but I probably wouldn't recommend it in general. Because if I had something like 5x to the minus 1/2 y to the 3 z to the minus 6 over 7 to the minus 2 x to the 3 y to the minus 7 z to the minus 4, and then I raise that to a -9. What I see happens all the time is students try to write this whole thing over 9. They try to flip the insides while moving things up and down. So technically switching locations is you can do that. So you can actually flip the inside and change it to a +9 power on the outside, and then move the locations of the x's and y's. So the x to the -1/2 could be moved to the bottom, the y to the -7 could be moved to the top. You'd switch the positions of the z to the 6 and the z to the 4. But when students are doing these flipping things and are moving things up and down, they tend to make a lot of errors, whereas it's much easier to do this problem and not make a mistake if I just subtracted the powers of the x, subtracted the powers of the y's, subtracted the powers of the z's, and keep those all inside the parentheses. You would tend to make less errors, right? So yeah, so a problem like this, I can tell you from experience that students who go with the position of, you know what, let me switch things based on the fact that the power is negative, I can move things up or down or flip things. They tend to make more errors than the students who just, you know what, this is x to the -1/2 divided by x to the 3, let me just subtract the powers. And they'll tend to always get the correct powers at the end of the day. Whereas when you switch things, you can forget to switch some things. It's too many things going on. Right, you do want to keep each operation as simple as possible. So yeah, it is possible to do that, and it would be correct to do that. I wouldn't recommend it though. I would much rather you subtract the powers than worry about switching locations of something.
Right, it just adds more steps, I guess.
It adds another thing for your brain to worry about. You know what I mean?
Okay.
So your brain is worrying about combining the powers while at the same time switching the roles of the positions. Right? It's an extra step. And yes, with one thing, you're not going to notice how much extra taxing on your brain that is. But trust me, when there are a bunch of things that you're moving around, it gets more complicated quickly. To keep things based on the rules that I gave you for laws of exponents is a lot more efficient, and it causes you to make errors. And that's just something that you'd want to keep in mind in general. In general, if you have 2 methods for how to do something, choose the method with the least bells and whistles. Cognitively speaking, it'll make your life a lot easier, right? So you can have 2 things that are just as both ways are correct, but don't choose the way that causes you to do 2 things at once instead of 1 thing at once. It's usually not worth it when the problems get too complicated. What about this one? Simplifying the radical expression. Ideas? What will the first step look like?
12.
So if I have 1, 4, 4, y to the 6. So thinking as a basic rule, what can we do here? You have a radical of two things multiplying. What does that mean?
You could see like that 144 is a perfect square.
Okay.
Take y to the 6, and I think that becomes 3.
Yeah, we're thinking too complicated. Just keep it very basic for me. Give me baby steps.
You can separate them and just do the square root of 144 and then the square root of y6.
Right. Because a radical is a power. You can distribute a power across a product, right? So when you see that, probably the first thing you're going to want to do is to just actually separate the radicals. Now, the radical of 144 we do know is 12. What is the radical of y to the 6?
Since
Wait.
it's an even power, wouldn't
Mhm.
you get like an absolute value?
Correct. Absolute value of?
Would it be y cubed?
Right. So these are some important things to remember. So let's talk about this. Radicals are powers. Note, radicals are powers. So they follow the laws of exponents. So that's the first thing that you should know. So when I have the radical of 144 y to the 6, this is the same as 144 y to the 6 to the 1/2 power. So there's a 1/2 power that I can move and put on top of these things, right? Now, of course, how would you actually calculate that? Well, this guy's 12 squared. And so you can take the rule where you multiply the powers. And so that would give you 12 to the 1 times y cubed. However, there is some nuance here. And that nuance is something that's often forgotten, but I did mention this in class, which is why I threw this problem in the quiz to see if you guys were paying attention. But there is a nuance here. Because radicals can have a peculiar behavior based on whether the things that are underneath them are negative or positive. So if you have an even radical, then you have to have something non-negative under the radical. Whereas with odds, you don't need this. So this leads to a very important nuance that I don't want you guys to forget. If you have something that looks like this, you have a radical and you have a power, you should recognize that it gives you the absolute value of x if n is even. And it gives you x only if n is odd. Okay? And the reason is because the even power is going to kill the negative, right? So let's see an example of why we have to worry about this. Example, look at the square root of x squared versus the cube root of x cubed, right? So let's look at these two scenarios, right? In the first one, the radical is an even radical and I have an even power. In the second one, it's an odd radical and I have an odd power, right? What's going to happen here? Now let's say x equals -1. Now, if I take the square root of x squared, that is going to be the square root of -1 squared. -1 squared is 1. And so this gives me +1. If my x were +1, then it gives me +1 again. So notice that the effect of doing this is actually getting rid of the sign, right? And so, and notice this behaves like absolute value of x. If I take the absolute value of 1, I get 1. If I take the absolute value of -1, I get 1, right? This function actually outputs exactly the same thing. In fact, this is an alternative definition for absolute value. Right, which I did mention in class. There are two definitions for absolute value that you must know, and one of them is this. It's x if x is positive, 0 if x is 0, minus x if x is negative, and you can think of this as the square root of x squared. Right? Now, one definition might be more convenient than another at some point, but especially even as early as Calculus 1, knowing the definition on the left is going to be super important. So the left one is the more important definition, but you should have the awareness that the second definition also applies. And so let's look at something else here. So what if we did something like the square root of x to the 6, right? So something like what we had before. What I can think of this as, well, x to the 6 is just kind of x squared, x squared, x squared. So that's just the square root of x squared, square root of x squared, square root of x squared. So that's just the absolute value of x, absolute value of x, absolute value of x. And so that gives me the absolute value of x cubed, which is the same as that. So that's where the absolute value is coming from. So once your power and your radical is even, you have to throw in an absolute value, because what happens is if your x is negative, the even power is going to make it positive. And so it gives you a magnitude. It gives you a positive magnitude no matter what, right? Whereas with the other one, with say the cube root of x cubed, if our x equals -1, if I take the cube root of -1 cubed, that is just the cube root of -1, which is -1. So that's just the original x. If I have my x as +1, that is the cube root of +1 cubed, which is the cube root of +1, which is just 1, which is the x. So we have that the cube root of x cubed is always going to give you x, while the square root of x squared, let me put that in here. While the square root of x squared is always going to give you absolute value of x. So for this one, the actual number that I plug in is the number that comes out. If I plug in a -1, a -1 comes out. If I plug in a +1, a +1 comes out. The cube root of x cubed is the same as x. Whatever I plug in, I will get out. This is not true with the square root of x squared. If I plug in a -1, a +1 comes out. It changes the sign. In fact, if I plug in any negative number, the positive value for that number comes out. That's exactly what an absolute value does. And yeah, that's why this is the answer. And that's why this is the answer. So I did talk about this in class, but I don't know if a lot of people are paying attention to it, so I made sure I put it on the quiz so that you can now it's something that you should think about all the time. So if you have an even radical and an even power, an absolute value comes into play. Okay, let's look at this one. How much time do we have? Okay. So here we're looking at simplifying radical expressions. And there's a strategy here that I do recommend in class in general. When you want to simplify radicals where there are a bunch of different bases. And that trick is to just split each radical into two individual radicals. And then in the first set, put the things that will simplify, and in the second set, put the things that won't simplify. And the definition of simplify is the radical would divide into the number on the radical will divide into the powers. So if I look at 5, the 9th root of x to the 10th, y minus 4x times the 9th root of xy, what I would do is in the first set, break it up into two radicals. In the second set, break it up into two radicals. Okay, and now what you do is you split these. So here, this guy here, I break it up into these two. This guy here, it's not necessary here, but I break it up into this two. Not necessary though, but we'll see why. Now, I need to split each individual into things that would simplify under a 9th root and things that won't. So here I have x to the 10th. I want to write this as a product of two x-based values where I get the largest power that's divisible by 9 on one of them and the remainder on the other one. So if I have x to the 10th, how can I break that up into two such things? If I want to write it as x to the something times x to the something else, that when I multiply them, I get x to the 10th, but I can split them up in a convenient way. Do we see a convenient way here?
X to the 5th and x to the 2nd.
Well, x to the 5th and x to the 2nd would not work, right? Because if I have x to the 5th times x to the 2nd, that's x to the 7th.
Oh, right. Okay, sorry. X to the 5th, x to the 5th.
Okay, so let's say I broke it up into x to the 5th, x to the 5th. If x to the 5th is under a 9th root, does that simplify? I mean, does the 9 divide into the 5?
No.
No. So that's not how I would split them up. Can you think of another way to break up 10? Into a way that would simplify with the 9th root?
Would it be 10 and 1?
10 and 1 cannot work because if I have x to the 10th times x to the 1, that's actually x to the 11th.
X to the 9th and x to the 1st.
If I have x to the 9th times x to the 1st, that gives me x to the 10th. So those are possible. Now, are they useful? If I put x to the 9th here and x to the 1 here, does that simplify in the first radical? It does, by the rule that we had before, right? X to the 9th, the 9th root of x to the 9th is just x. So that actually simplifies, right? The radical actually divides into that power. So that's good. What about the y? I have y to the 1. Can I split that up in a way that simplifies and one that doesn't? Well, not really. I mean, it's just y to the 1, right? That's not going to simplify, right? Like I can't break off a positive number that's divisible by 9. It's just 1. So the x, I can split it, the y's I can't. Similarly here, they would both be over here, x to the 1, y to the 1. Nothing would simplify from those. So yeah, that just wasn't worth it. However, here, this part here now simplifies to x. So we have that. Anyone see what we can do now? So I have 5x to the 9th root of xy minus 4x to the 9th root of xy.
Subtract negative 4x from 5x. Or sorry.
Yeah. So what would you get?
Sorry.
I mean, this whole thing is the same, right? So it's like, so if let's say I call this A and call that A, what I have is 5A minus 4A. How would that simplify?
Just the
A, right? If I have 5 apples minus 4 apples, I'm just left over with 1 apple. So I'm just left over with the thing that's in green. And that's your answer. And that's choice C. Okay, so there's this thing about simplifying radicals. How you can do it is to just break it into 2 radicals. So let me do an additional example here to make sure that we get it. If I wanted to simplify, let's say, the 5th root of, what's a nice number here? Let's say 64, x to the 17, y to the 23, z to the 15. Okay, so remember how we'd go about simplifying that? Well, you immediately break it into 2 radicals. Over here, you're going to put factors that simplify. Factors that don't simplify. Simplify in this situation has a very specific meaning. Simplify means the number on the radical divides into the power. Okay, so now think of 64. Can I break it into 2 numbers that when I multiply them, of course, I get 64, but each individual factor behaves differently. One is simplifiable when I take the 5th root, one is not. 64, how can I break that into 2 numbers? One I can take the 5th root of and one I can't.
Ooh.
I mean, if it helps, you can know that 64 is equal to 2 to the 6th, if that helps. Does anyone see how we can break that up? Two to the something times 2 to the something else, where the first something is divisible by 5.
Two to the 5 times 2 to the 1.
Right, 2 to the 6 is the same as 2 to the 5 times 2 to the 1. I put the 2 to the 5 in the first one because that'll simplify. 5 does divide into 5. I put the 2 to the 1 in the second one because it doesn't simplify. 5 doesn't divide into 1. Right, so that's the first thing. Now what about the x's? I have x to the 17th. Break that up so that one is simplifiable, one is not.
You could do x to the 15 and x to the 2.
You can do x to the 15 and x to the 2, right? The sum is 17, and 15 is the largest part of that sum that's possible that I can simplify. It's worth mentioning that if I had done something like 10 and 7, that is also technically correct. However, the x to the 7th can be simplified further. I can get an extra x to the 5th out of that. So you do want to break this in such a way that the largest possible simplification can happen, which means I would break this into 15 and 2. What about the y's?
You can do y to the 20th and then y to the 3rd.
Right. What about the z's?
Couldn't you just leave it as z to the 15th?
Where does the z to the 15th go? In the first radical or the second?
The first one.
Right, so that you move all 15 over here. Technically, you have a z to the 0 here, which you don't even have to write them down. Because it's just 1, right? So now, you'll notice that the first one is going to simplify. I can take the 5th root of everyone here by just dividing the powers, because the 5th root just means the 1/5 power, and I can distribute these powers. So this just becomes 2x cubed y to the 4th z cubed. And I'm left over with 5 times 2x squared y cubed z. And that would be the simplification. I can move certain things outside the radical and get a smaller radical resulting. This is called simplifying the radical. And I think an easy strategy to do this is just break it into 2 radicals, move all the factors that simplify into the first one, move all the factors that don't simplify into the second one, and then you simplify the first one and you're done. Right, so that is the strategy that I did here.
Can you scroll back down to the answer? Why is there a z under the radical in the final answer?
That should not be there. Which is why you don't write. I saw the z in the corner of my eye. Okay. Simplifying radicals, another important thing. And at the end of the day, we're still at the stage where, I mean, at this point it's going to be challenging, but you really want to nip it in the bud at this point, because everything we're doing so far, it's the sort of thing that when you get to calculus and beyond, people are going to expect you to be able to do these on the fly, kind of like in the background of your mind, because you'll be focusing on solving other problems, bigger problems. So it's very important that you get very quick with this and you just know the rules, right? You know when you add powers, when you subtract powers, how to simplify a radical, how to do this, how to do that, because they're going to be doing all these things while doing other things. So be very careful with the rules. Okay, suppose I have an expression with 3 terms. I want to factor it. What is the first thing you want to do? I actually asked a problem very similar to this on quiz 1. What is the first thing? Right, so you have no information other than what I just told you. I gave you something with 3 terms. You want to factor it. What's the first thing?
Wouldn't you want to find the 2 numbers that multiply and then add to give the middle term?
No. Why would that be the first thing? Let me show you why that's not the first thing. So let's say I had 2x squared plus 3x plus 5. Would you find 2 numbers that multiply to give you 5 and add to give you 3 to factor that?
Oh wait, I get it. Never mind.
Right. You'd have to do something else. You'd need like the AC method. Technically, you'd want 2 numbers that multiply to give you 10, and they add to give you 3. So but now you guys, I said 3 terms, so you're probably thinking quadratic, but I never mentioned it was a quadratic, which means if I asked you for this one, yeah, the first thing you would do is think of 2 numbers that when you multiply, you get 5, and you add them, you get 6, which 5 and 1 would work. However, if there was a 5th term here, that strategy doesn't work anymore, right? So be aware that I never mentioned that this is a quadratic, which means it's possible that I gave you something like this. So what's the first thing that you should try to do? I'll give you another hint since we're running low on time. It's literally the first thing you do always, right? So when we had a class about a general approach to factoring, how to approach any factoring problem in general. There was a first thing to do in every case. What was that first thing? GCF. Factor out the GCF. It's always the first thing. All the other strategies I gave you, they're very dependent on how the thing looks, right? So if I told you that something is a quadratic, then yeah, you'd still actually look for a GCF, right? So if I gave you a quadratic 4x squared plus 8x plus 4, your first step would still be to factor out the GCF. You still wouldn't go into the position of, oh, let me try to find two numbers to multiply, blah, blah, blah. So even if you have a quadratic, the GCF is still the first thing you would look for. If a GCF exists, you need to find it first and factor it out. It's always going to be the first thing, right? So it was an answer choice on quiz 1. Here I didn't put it as an answer choice, but it is none of the above, right? Because on the other quiz, I had to make the question different somehow. But this also goes into something that I was mentioning to you guys before about being aware and knowing about what information you have. At this point, I didn't tell you it's a quadratic. You cannot assume it's a quadratic, right? So you have to be aware that I said a general expression, right? Now it turns out if you have no information, you default to the first step that you always would take, find the GCF. So all of these options here are kind of things that you would do if you knew it was a quadratic, but we don't know it's a quadratic. So these may be applicable for specific quadratics. So if this question were rephrased and I were to ask you, what if I gave you a quadratic where the leading coefficient is 1, how would you go about factoring it? Then option C would be the correct choice, right? If I said, oh, what if I gave a quadratic where the leading coefficient was not 1, then option A would be the right choice. The fact that I just told you 3 terms and no other information means none of these are now the right choice because you don't even know if it's a quadratic in the first place. We're sort of running low on time, but I think a lot of these nuances are things that are very important to pay attention to. So this one I actually covered in our review session. What was the answer? In the review session, I gave you the example of x to the 6, y to the 6, but it's the same idea. Do you guys remember? What you would do first?
Wouldn't it be answer choice B because it's like simpler than doing the cube root,
right?
And it would get all the answers.
Right, and this again falls in line with the advice that I gave you earlier. Choose the strategy with the least bells and whistles, or with the lowest level. So you would try to apply difference of squares before you try to apply difference of cubes. Okay, so continuing with this problem, if you fully factor that, what would you get? So I guess at this point, you would have to just fully factor it. So if you have x to the 12 minus y to the 12, like I said, the first thing we would look at this as is x to the 6 squared minus y to the 6 squared. This is difference of squares, so this is x to the 6 minus y to the 6. X to the 6 plus y to the 6. Now, the first one is the difference. I can think of that as a difference of squares again. So this one I can think of as x cubed squared minus y cubed squared. This one here, there's no sum of squares formula. However, there is a sum of cubes formula. So instead, I would think of this as squared cubed plus y squared cubed. So this would break down into x cubed minus y cubed times x cubed plus y cubed. Over here, this would be x squared plus y squared times that squared plus this times that, not plus, minus, plus that. And then I would apply the cubes formula here. So this is x minus y times x squared plus xy plus y squared. This is x plus y times x squared plus xy minus plus y squared. This here would be x squared plus y squared. Can't factor that anymore. This is x to the 4th minus x squared y squared plus y to the 4th. So we have 1, 2, 3, 4, 5, 6. And that's how we'd fully factor this at this point. Let's keep going. So we'll do one of these. I'll leave the bonus for you. Well, you guys know the answers to the bonus already, so try to work those out. And maybe next time you can actually if you have questions on that, next time you can ask me. That's this one. So again, that's just a formula that you should know. That's the expanding a perfect square. Okay, so this one is again kind of expanding a perfect square. And I did mention, so this is sort of connected by the same strategy. That's why they're in the same parts. So if I worried about what a squared plus 6a plus 9 would factor as, well, that would factor into a plus 3 all squared. And then what you think about is you can just attach a b to each of these parts. So attach b after. Another strategy I spoke about in class, so nothing much to go over here. So it would be this option here. And then finally, 10.3, the last non-bonus problem. These problems here will be dealt with in future lectures that you're supposed to be watching, so we don't have to go through those right now. But after watching the lectures, you can come back here and try them and see if they would work. For this one, the hope was that you would have noticed that this is something that was factored in the previous step. So here, this is a squared plus 6ab plus 9b squared minus 49. This is equal to, by the previous step, This is equal to a plus 3b all squared. 49 happens to just be 7 squared. And so here we really have a difference of squares. So it's the first one minus the second times the first one plus the second. So this is actually factors into a plus 3b minus 7 times a plus 3b plus 7. And that's the first option. So it's a weird factor by grouping where you group the first 3 terms instead of the first 2 terms. But yeah. So at this point, I'll leave the bonus up here. You guys can already see the answers to the bonus in Gradescope. But at this point, you won't, in theory, some of you might know how to do this already. But in theory, no, you wouldn't have known this because you wouldn't have watched the lectures at the point of at the time of the quiz. So maybe watch the next 3 lectures and then look back at these bonus problems. I'll leave them in the PDF of the notes, and then you can try them. And that's it. We're a few minutes over time, so I guess we can let go at this point. So we'll wrap up right there. Thank you for your attention. Thank you for your questions and inputs. But we will pretty much stop there. So yeah, and that's all we have for you today. Remember to check the schedule on the class webpage so that you know what lectures you should be watching today and the plan for next week. That being said, bye everyone. Have a good day. And I'll see you guys in the next one.
See you.
Thank you.
Out. Take
Thank
care.
you.